Okay, so today we're going to talk about sequence of operations. We've kind of been touching a little bit on some sequence of operations type things. We've been talking about refrigerated cases. We're still talking about that, but we're going to slow down a little bit today and talk about what's happening in our circuit as we enter refrigeration, as we enter cooling cycles versus defrost cycles. And take a look at what's happening in our circuit in each step along the way. So a sequence of operations, I think we've discussed this in maybe some of the past modules, but that basically is the order in which things happen. Things have move. You have component A is in state X, and component B is in state Y, then component C shall be in state Z. And when things start not working correctly, it's because something in this sequence is not happening correctly, which is causing something else in a system to not function properly. And then this is where service calls will start to be generated. So we'll just very quick explanation of defrost and cooling sequence of operation. We have obviously a cooling cycle and a defrost cycle. The defrost cycle will initiate at a pre-programmed time. When it's initiated, the fan circuit will open. Liquid line solenoids, EEPRs or EEVs, they should close to stop the flow of refrigerant. The defrost relay will close in order to provide power to the heating element in the first place. The defrost cycle will run for a specified duration, or it will terminate early based on an input from a sensor or some sort of sensor. And then a drip cycle will be initiated, which basically just means a time delay before fans turn on is all that really means. And when the defrost cycle terminates after the time delay, fans will turn back on and the space will start to be cooled again. And obviously in the cooling cycle, we're cooling. So we should have fan contacts closed. Our liquid line solenoid will be energized. And we'll be pushing air back into the space or the case or whatever the location is there or piece of equipment is that we're trying to cool down. So I thought it would be useful today when we're talking about sequence of operations, to look at it from the perspective of a more compact system. What we're working in supermarkets, you've got a rack house that's located many hundreds of feet away from our equipment. That typically has its own controls for the compressors that aren't directly interrelated with the controls at a local case, right? The compressors in a refrigeration or in a supermarket is responsible for pushing refrigerant throughout an entire store that will serve cases that are in various states of defrost or cooling. Right? We're not controlling the compressors locally at the case level. So I thought it'd be useful just to sort of shrink this down and maybe talk about it more from the perspective of a self-contained case. And so in the case of with a self-contained case, we may see something that looks more like what's on the screen here, where we have a mechanical time clock. There may be some sort of bulb style thermostat here on the right. And instead of sophisticated programming, in order to set your defrost timers, now we have a more simple construct here, where you have a time clock. We all know what clocks are. And we have these pins that represent 15-minute intervals that we can set a defrost time to. And then we may have a thermostat, something like this, that will provide our early termination set points for killing the circuit to the defrost heaters early, and then providing some time delay for the fans to start back on. And then in the case of a local compressor, we may have two of these. There may be one for early termination of defrost and one for control of the compressor itself, just to maintain the refrigerant at the right set points. And so here's the wiring diagram for a mechanically controlled cooling system. I just pulled these off of the old internets, and we have the defrost wiring diagram here. But you can see this has got 10 different configurations that we might see in a self-contained case. This could these mechanical time clocks could be used for walk-in coolers also. So anyway, yeah, I just wanted to show that we have there could be several different configurations. So this isn't too different than what we might see just in what we do from day to day, where there's a lot of if thens, like what components are we going to have, and typically as the electricians, we aren't the ones determining what parts are going to be in the system. That's going to be designed for us most of the time. But if we understand the sequence of operations, then we can then reason out what's happening in a circuit in order to diagnose what's wrong and to repair it. Or maybe we do come into a situation where we have been hired to do the entire design and installation of a walk-in case. There's no engineering done. Well, we can figure that out and just follow one of these schemes and work with our refrigeration teams to determine which one of these configurations we should be going by. I just blew this up so that we can refer back to this as we move along. It's just the various terminals on a mechanical time defrost time clock. So these terminals here that are labeled F3, 1, 2, 4, N, and X. Just wanted to blow this up because we're going to refer back to this several times. Okay, so we'll talk about the mechanical time clock just for a minute so that we can know what we're talking about as we move forward. So the mechanical defrost timer consists of multiple terminals. You have there's terminals for the compressor, there's terminals for the evap fans, and the defrost heaters as well. So if we go back to this diagram, we can see that we have terminal F, which isn't being used in this diagram, but this could be used for your evap fan. You have terminal 3, which is connecting to one side of your defrost heater. The other side of your defrost heater is connecting to L2. You have terminal 1, and this is where your line voltage would be coming into terminal 1. But it's also in this configuration, there's a jumper over to terminal 2. So the same power is feeding on terminal 1 and 2. But you could have a situation where perhaps this is a different circuit coming in, or there are other configurations where that breaks, such as this 3 here. It's just a different control scheme. And we have terminal 4 here, which is responsible for delivering power to the compressor. So in a self-contained case, the compressor would be sitting up on top of it. So we would need this contact closure to provide power to a thermostat that then controls power to the compressor. So there's a thermostat in this diagram in series with the compressor to control that locally at the compressor. And also to the fan motor, we have terminal N here, which is bringing in our other line side of our circuits. Well, in this circuit, it looks like it could be a 240 volt circuit. Line 2 is coming in and terminating on N. Now this could confuse electricians who are used to using neutral. You look at N and say neutral, but you could sort of look at that the same way. L2 is coming in, landing on neutral, but also this could actually be neutral if this were a 120 volt system, which I don't know how common that would be to see, but certainly, well, refrigerators in our home, right? That's a self-contained system, 120 volt. Those probably have microprocessor type systems in them, but it could be controlled by a mechanical system like this as well. So that could be neutral. But so you could think of this as neutral, line 2. Either of those would be fine to think of this about in this type of time clock. And then in this configuration, also we have a termination thermostat with fan delay. So this thermostat will be responsible for early termination of defrost in order to allow the compressor to come back on. And then after a delay, which basically just means that this thermostat will return to its opposite set point. So instead of its set point of termination set point, it'll return to its cooling set point, and then it'll allow the fan motor to run. So those are the terminals of a mechanical time clock. Okay, so defrost, when we go into defrost mode, what's happening? So when the pins are out, the unit will be in defrost. So what does that mean? So we have these pins on this mechanical time clock. This is akin to programming an S3C controller for a set point of when they're going to run. This is the same thing. This is sort of like the carburetor version of fuel injection, right? Where you can go in and you can mechanically set your throttle and all that. In a carburetor, this is sort of similar, in terms of like this level of sophistication. You just you can set these pins, and then as this time clock turns, the pins that are out will come in contact with a mechanical switch inside the timer, and then change the state of the timer. So when pins are out, the unit will be in defrost mode, and when the pins are in, the unit will be in cooling mode. So it's whatever duration that you're setting that up for. And we can see the termination is just shown for us here across 1 and 3, and then your refrigeration across 2 and 4. Looking at this diagram and thinking that every time, the point is not to say that to understand like how this particular time clock is wired, because you may have different models, and then the terminals might be in different spots. But although I think this is fairly common for mechanical time clocks.
So let's take a look at what's happening when we enter defrost mode. So when we first enter defrost mode, so the time clock has reached its set point that would initialize defrost. The fans, liquid line solenoids, and compressor all needs to be de-energized. So if we go back and look at our wiring diagram for the default wiring configuration, and we follow power along L1, we can see that when we initialize defrost, right now the diagram is in its cooling configuration. So we can imagine that these switches, so this terminal that goes from 2 to 4, that switch will change position. So that will, when that changes position, power will no longer be able to get to the compressor, right? And then we see the terminal between 1 and 3, that switch there will also change position. So if the fan were terminated on F, then that would kill power to the evap fans as well. Since our fan in this diagram goes from 2 to 4, and our fan motor is wired off of terminal 4, then that same contact opening off of between terminal 4 will also kill power to the fan. And then at that stage, our defrost heater will receive power because our terminal from 1 to 3 will have changed to the opposite position, allowing power to go into the defrost terminal. Now when defrost is finished, one of two things is going to happen in order for defrost to terminate. Either the time clock is going to time out, so we've set it to 15-minute intervals, we have passed the time for those 15-minute intervals. Now all of our switches are going to return to their original positions. Power will return to the compressor, and power would return to the fan motor if it were just terminated off of the time clock alone. But sometimes you'll have an early termination of defrost, and that will be initiated by this termination thermostat with fan delay. So we have this thermostat here that goes between terminal X and L2. And so if we follow that along L2, we can see that we have a 3-position switch here. And if this which is the thermostat, and if that thermostat reaches its set point for early termination, so it should be sensing that the heating element or that evaporator coil has reached a heating temperature threshold for this thermostat, power will be sent to terminal X to initiate an early termination relay on our controller. And so when that happens, that will return the contacts to their normal positions for the compressor and allow power to be run back to the compressor. It'll allow power back to one side of the fan circuit motor. But since it's a thermostat, what's going to happen is that compressor is going to turn on. It's going to flow refrigerant for a while, which is going to cool back down that evap coil. And when that evap coil cools down enough, this thermostat will then go back to its previous position, its cooling set point, restore the other side of that fan circuit motor, and then the fan will turn on. So this sort of provides a inherent fan delay operation to the circuit, simply because it is a thermostat in the circuit and you're not going to instantly change states there.
Okay, so the sequence of how this is going to work. Okay, so this timer, we've set the time. It hits at a certain time of day. Okay, we know we want defrost circuit time to be, let's just say 12 o'clock. Okay, at 12 o'clock, we want defrost to run for 1 hour. So this is going to hit its set point for defrost. When that happens, right, this time clock, these contacts are going to change position, right? This is going to open, and then this contact is going to close. So what's happening when that happens is we are killing power to the fan. So we can see that power along line 1 here is coming up 2, and this contact will open. So that's going to kill power both to your evap fan and to your compressor or solenoid or contactor. Any one of those things or all of those things could be coming off of this number 4 terminal, right? So fan motor, compressor, those will be de-energized when we enter defrost mode. But then also this other switch coming off of 3 is going to change position and then initiate defrost. So your defrost heater here will turn on, right? And then so fans are turning off, compressor's turning off, defrost is turning on, right? That's pretty basic, right? That's going to be when we enter defrost. So I think that's what this was trying to tell us. This is more of a termination sensor than a fan on sensor. So I think we need to adjust that slide. Okay, so this is just showing us what's happening when our liquid line solenoid is energized or de-energized rather. So when it's de-energized, it will go into its closed state and stop the flow of refrigerant. Obviously, when we are in defrost mode, we don't want to be fighting the system that's trying to simultaneously cool down, right? And so our sequence is, now that we enter defrost, our liquid line solenoid should de-energize in order to stop the flow of refrigerant. Here's an illustration of what that looks like on the inside. Although I sort of feel like this illustration is incomplete because the right side of this liquid line solenoid is the same, or this is an EPR, but it's sort of the same. But you can sort of see how the chamber here is filling up in its energized state, which implies that we're allowing refrigerant to flow through it, versus its de-energized state, which is blocking refrigerant. So when the defrost relay contacts close, we're allowing current to flow to the heating elements. So, okay, so I'm going to just ask the question, look for a response. Just somebody, don't be shy, but what position should the fan, liquid line solenoid, and compressor be? What position should those contacts be during defrost mode, open or closed?
Open.
Yeah. I actually kind of wrote this question wrong. So the fan and compressor, those should be open, right? We should be killing power to those. The liquid line solenoid should be closed. And why would that be? Why would the liquid line solenoid be closed, whereas the compressor and fan contact would be open?
I mean, the circuit would be open, wouldn't it? Because it would be de-energized.
So the liquid line solenoid is sort of like a reversal in how we're thinking about it, at least when controlled locally at the case. When we're talking about out at the rack house, I believe I was told that those are different. But mechanically, when the liquid line solenoid at our cases are a normally closed, it's a normally closed valve.
Right.
So
But
when
the
it's
circuit would be open, correct?
so it's sort of opposite. So like when we're energizing the liquid line solenoid, we're closing. No, we're opening. Sorry. See, it's hard to. Yeah, this is something you got to stop and think about, right? So we want to provide power to the liquid line solenoid when we don't want refrigeration to flow.
When
Right.
you get a solenoid that's energized, it is open.
It opens the valve.
When it de-energizes, it closes the valve.
When it de-energizes, it closes. Right.
Yes.
Yeah.
Because it's normally, the valve's normally closed.
Right.
It
Yeah.
stops.
So when it's de-energized,
It's closed.
we are not providing power to it. We provide power to it to open it.
Correct.
Maybe I'm just getting that mixed up in my own head. Well, that's a lot more simple in my brain.
Yeah, because I think of it like this: when we pull vacuums, we have to have a magnet in order to open it up
Mm-hmm.
to complete a vacuum. So it normally comes closed. And in
Oh,
order to open it, we got to use a magnet.
okay. I had that more
But when you
complex
put
in my
power,
brain.
you put power to it, it's going to open it. And when
Okay.
it energizes it, it closes it.
Oh, that's a lot easier for me to think. Uh, hey, so when we want cooling, provide power to it. Okay, so that's the opposite though. So we're providing power. Okay, good. We can slow down. We can talk about. Help me understand this
Yeah,
better. Then help me.
de-energize means no power to it, and it shuts the valve.
Okay.
When it comes out of defrost, there's power applied to it, and it opens it up to allow refrigerant to go through.
And then our fans. So where we provide. So we're not providing power to fans.
Well, it's depending what application, whether it's frozen or medium temp. Because frozen,
Oh, we're talking about frozen here because
You're
we have a
frozen.
defrost cycle here.
You're right. Your fans will shut off when it goes into defrost.
It's typically that solenoid circuit is tied to the fan circuit, correct?
Okay, yeah. So we're doing this. Okay, I don't know
Yeah,
why I was
yeah.
complicating that in my head.
Okay,
Yes,
let's back up a minute.
Yeah.
That previous question you had on that slide was asking what's going to happen to the liquid line solenoid fans and compressor.
There it is. Yeah.
Okay, so basically what that's going to do is turn all of those off, even though the power supply may be different. Maybe that's a better way to explain that.
Mm-hmm.
So your fan, your liquid line solenoid, and your compressor are all going to shut off.
Mhm.
Now the fans, liquid line solenoids, are typically on a normally closed contact, and the compressor could be normally open. So you have to do two different things to make that happen. And to Robert's point, yes, the liquid line solenoid is typically at the case level fed by the same common power source as the fans are.
Okay.
You
Yeah.
may have opposite acting processes to make both of those or all of those things go off. So you do have to, like Phil said, you do have to think about what you're trying to do and then figure out what has to happen to make that happen.
Right. So electrically, all of these are the same contact types. These would all, if your fan, liquid line solenoid, and compressor, if you need electrically, you need a contact closure for them all to run. Then so they'd all be normally go from open to closed. We just open those contacts. I don't know. In my mind, I guess I was sort of thinking, okay, maybe the liquid line solenoid is normally closed, whereas the others are normally wired to normally open contacts. But I think that's where I was getting myself messed up. If we can go, let's go back to this diagram here and just make sure that I'm not a crazy person. Okay, so this is right now it's showing in cooling mode, right? This is its default state. It's in cooling mode. So we got line 1 coming in. We're providing power to the fans, fan motor, and the solenoid, and the compressor. So yeah, we're just reversing that. When it goes in defrost, this opens. We kill power to the fan, compressor, solenoid. This also will change position in order to provide power to the defrost heater. So that's simple. Okay, I was complicating that.
I do it all the time.
Yeah, I did. Yeah, man, I don't know. I overthink, over design, and then half the time I'm like, oh, I'm out in left field on this. Bring me home.
I do it too.
Okay. So where are we in the cycle? We are in defrost. Our time clock has initiated defrost. We've opened our power to our fan with line solenoid and compressor, and it's going to run for its one of two things is going to happen. Either it's going to run for its full pre-programmed time duration, or it's going to run until the early termination is initiated. Okay, so in the S3C controller, that early termination sensor is provided by a resistor style input, right? We talked about that last week, where we read the changing resistance as temperature changes, and the solid state controller understands that to mean that heat or cooling is either increasing or decreasing, and then we'll either initiate, and then we'll kill defrost based on that. In the sense of a self-contained case, or at least in what we're talking about, we might see something more like this. And so this, there's a bulb here. I don't know what's in it, but some sort of material that would expand or contract depending on the temperature, which would push on a spring inside this thermostat, which will provide a contact open or closure across a form C contact. And so that's this guy right here. So we can see power from L2 is feeding to the common terminal on this thermostat, and in cooling mode, it is closed and allowing power to the fan motor here. So your evap fan will run. So our defrost cycle has completed, or at least we have stopped providing power to the defrost heater. So what initiates that, at least in this circuit, is this thermostat will hit a certain set point to say, okay, we've met our max heating set point. This will change position, and it will hit this termination relay, which I guess is one of these guys, right? Probably one of these guys on the board, right? And then all of these other contacts will return to their previous state. And so the compressor will be allowed power. We'll be finishing the circuit to one side of our fan motor at this point, and we will stop providing power to our defrost heater. But this being a thermostat, it's not going to return back to its other contact point right away, will it? There'll sort of be a natural time delay with that. As this compressor turns on and starts pushing cold refrigerant through the evaporator, this sensor is now going to move back in the opposite direction. And then once it hits its opposite set point, it will close again and then turn power onto the fan. I've seen that referred to as the drip cycle. And why do we think that might be called a drip cycle? Anyone who is actually in refrigeration might be able to tell me better. But
So that's the drip cycle is when defrost is terminated, that gives you, and it can be set anywhere from 1 minute to 5 minutes to 10 minutes to whatever the case may be, to allow the evaporator to drain all the water off the coil before refrigeration is initiated again to keep it from icing up.
right. Yep. So yeah, so that there's sort of like in the sense of this system here, like what I was thinking is this thermostat, there's going to sort of be a natural time delay while until this gets to the right cooling temperature to move it. So I guess two things are going to happen there. One, you're going to allow time for it to drip before you turn fans on, and then push those droplets of water out into a space. Like you really wouldn't want to be doing that like in a walk-in cooler, right? We just have defrost. We have these droplets of water on the evaporator. If you turn the fans on right away, you're going to push water out into the space. It may end up on the floor, and then you've got a slippery surface on the floor. So this will allow time for that to drip off. Also, because we're not flowing air through it, it's dripping, but also isn't it frosting a little bit at the same time? Like it's refrosting a little bit. So now your droplets will sort of start to freeze, almost like, well, not almost, it'd be just like, I come from in Massachusetts, in our winters, we'd have to go and scrape the frost off of our windshields in the morning. Probably be something similar to that. To now your droplets are not in a state where you can push them out into the space.
Right, and it also just gives that time. You don't want that frost to build on that coil before, or ice to build on that coil before the fans in refrigeration come back on. That's where that drip time comes from. And yes, the fan delay can be the same thing. Keep it from blowing it out, because you can have an ice skating rink in those floors if you start blowing that water out of that coil.
Yeah, I've seen it, experienced that. Oh, in our refrigerated cases that are controlled by the S3C controllers, is that done programmatically? Or are they less concerned with that in a case?
They do have a drip time in some cases. Obviously, in that case, it's strictly to keep ice from building on the coil.
Okay, so this is just an illustration to show us the terminals that are responsible for that defrost, that fan delay that we're discussing here was on terminal X. Okay, so we kind of discussed that already. This, I don't know if this is actually called a failsafe, but this illustrates that many defrost controls have a failsafe that terminates the defrost after a program period of time if the defrost termination sensor does it. I mean, I don't know if failsafe is the term that you would use. It's just there, one of two things is going to happen. Either that early termination sensor is going to initiate and kill it early, or it's going to run for the pre-programmed duration, which would be, in this instance, like however many of these 15-minute set points were set. You could set this for an hour. It would run for the full hour. So it'd just be one or the other, showing where the termination would happen on an S3C controller. This would be where that resistor would terminate in order to effectively do the same thing, to provide early termination of defrost. Okay, so we finished our drip cycle with the electric heaters off. Open and restart the refrigeration while running the case fans. Okay, we have already talked about this. Okay, we kind of got ahead of ourselves, but we talked about this. Okay, so we finished our defrost cycle. Now fans are going to come back on. So when the fan delay temperature is met, the fans come back on and the unit resumes its normal refrigeration operation. And so as you can imagine, now we're not running defrost. We're simply providing fans, power to the fans, and the compressor, and things are going to operate as they should. Now with the compressor, there's still some control that's happening in this circuit, right? So we're just going to run power to our fans without any more control. As long as this time clock is closed, the fans are simply just going to run. But this compressor, they're showing a thermostat in series with the compressor, in the case of a self-contained case. So I would imagine that we would want to control that this compressor is not going to run. In fact, I know it doesn't, because I hear my refrigerator, it does this. It turns on and off all the time, but it's not going into defrost mode. And so this thermostat must be maintaining the temperature of, I don't know where it sits. If it sits on the suction line, I would imagine it sits on the suction line. Maybe Jason, do you know a little bit about that?
It can be both. It can be it depends on how the system's set up. It can run off a suction line and have a calculation for saturated suction temp that it's trying to meet, or it can actually have a discharge error returner or temp sensor in the case that runs it.
Okay, and so that would be with if it were like electronic controls, then it would be like we are used to seeing in our stores. You'd have some kind of thermostat. It's still a thermal input of some sort, or you might have something like this. I think I've seen something like this out at the rack houses at the compressors. Maybe a different form factor, but something similar out there.
Usually when you see those in the rack house, that's for actual exhaust fans in the rack house.
Oh, okay.
We rarely use a T-stat like that. We did before they came out with the KE2s. We would use a lot of those in walk-in coolers to control the temp, and that strictly controlled the liquid line solenoid.
Okay.
Just for temperature.
Okay. Okay, so maybe this illustration is showing a thermostat controlling the compressor. So what does control that compressor, like in the case of a self-contained case?
It would have, well, all our self-contains are electronic, but
Okay.
like it could be just as simple as a temp sensor.
Okay. Okay. So there's a temp sensor that's controlling this this compressor, because you wouldn't want that just running 24/7. If your evap's already at temperature, then there's no reason to keep pushing more refrigerant through it, because you got to maintain some kind of balance, right, of your vapor versus liquid. And so this sort of gets beyond the scope of what I can pretend to know. Yeah, so that's pretty much the full cycle by an electrician. But it's just sort of like looking at a system, right? We can look at this wiring diagram, and we have all these components, and having a little bit of an understanding of what each one of these does can help us to, like, sort of put it together, maybe do some diagnostics on this system. If we're trying to figure out why this fan motor isn't running, and we have this thermostat in the system, it's like, okay, we don't have defrost on. There's no power to defrost. We're not in defrost mode. My fan's not running. What would I do to figure that out? Okay, test power at the fan. Okay, there's no power at the fan. If there was power at the fan and the fan wasn't running, I could probably conclude that the fan is bad. But there's no power. So what's happening? Let me go back to this other component. There should be there's this thermostat in the circuit. Okay, let me see if that's changing position. What are the set points on that thermostat? Are they set correctly? If so, okay, well, are the contacts moving on that? And then you could diagnose this part and see whether or not maybe this part needs to be replaced, or maybe it's not installed correctly, or something to that effect. But electrically, this isn't a super complicated circuit. It's just spending the time to slow down. Like, I studied these slides this morning, right? So a lot of times we're going out to jobs, and we're sort of having to study what we're doing on the spot. And so it's sort of just trying to get used to that sort of that troubleshooting and reasoning out, okay, what's in the circuit, and then what is the sequence that it's going to run in. If defrost is on, then these other things should not be happening. And if they're both happening at the same time, then there's something we need to diagnose and figure out in the circuit to get it running correctly. That's about all I have to offer on this, which may not be much.